Hello. Okay, so we are live and we were solving graph problems. Yesterday we solved this problem round trip, and we'll look at monsters and shortest routes today. Okay, so this monster question, this is so the question states that we start from A in the grid and we have to move to the walls boundary square without encountering any monster, and if that is possible, print the path that you can follow. Okay, so the monsters can take one step as well, so this is kind of a tricky question. No, maybe it is a standard question, but I don't know the solution or how to solve this type of problem yet. So we'll go to shortest route. Okay, so N cities, M flight connections, length of the shortest route from Sirjala to every city. Okay, it is possible to reach Sirjala simply Dijkstra, right? Simple Dijkstra. Okay. We have weight given. This is basically a weighted graph. Okay. all the weights are positive, so there is no negative loop, so Dijkstra will work. Okay, so how Dijkstra work is that you start from a node. Let's see. Okay, so we start from it. Before that, we'll draw the graph. One is connected to 2, one is connected to 3, 3 is connected to 2, and one is again connected to 3. Okay, so 1 and 2 has 6 weight in their connection. 1 and 3 has 2 weight, and 3 and 2 has 3 weight. 1 and 3 again has 4 weight. So yeah, we will start from 1. We will maintain a priority queue. Okay, so first 1 will be pushed with 0 weight or 0 distance. Okay, because there is no distance, or basically there is 0 distance from node 1 to itself. Okay, then we will traverse in the neighbors, and we will push so basically 2, and distance will be distance to reach this node plus the edge, so 6. Similarly here 3 with 2 and 3 with 4. Okay, now work of this is done. We'll pop this out. Whichever one is the shortest, so this is the shortest, we will take this out, or we will start traversing from this node. Okay, so it has a distance of 2 right now. From here we can go to 1. This is a directed graph, right? It works anyway. So from 3 we can go to 1, but 1's distance is already 0, so 2 plus 4 6 is not visible. from 3 we can go to 2. Okay, so but 2's distance is already set to 6, so we will have a distance here also. So 0, 1, 2, 3. Okay, right now 1 is set to 0, 2 is set to 6, and 3 is set to 2. We started from 3, so going to 1 will cost me 6, or the distance will be 6. So 6 and 0, which is minimum, we see that 0 is already minimum, so we will not do anything. Okay, going to 2 from 3, we will see that it will take 5 units. The distance is 5. Okay, so which is minimum than 6, so we will update it as 5. After we have traversed all the edges, we will remove it, and then we see that we have 3 and 4. Okay, so we again start from here only, 3 and this 4. Okay, so reaching 1 from there is 8, which is not minimum. Reaching here will take you 7, which is not a minimum, so this is also processed. And then we have 2, 6. So from 2, where can we go? We can go to 3 or 1. Okay, so going to 1 again will give me 6, which is not less than 0, so will not do anything. Going to 3 from 2, it will take like 9, which is not less than 2, so we will not process. So finally the queue is empty. We have everything processed, and the distance array that we have with us is now like this, and this is the answer. See, this is the answer. So it's a simple Dijkstra. And we can either implement it with a priority queue or set. But the thing is, you see here in the first iteration itself, we had found the minimum distance, right? Then the next iterations with 3, 4 and 2, 6 were like redundant actually. They only will contribute increasing the time complexity, nothing else. So we need to remove unnecessary states, and in priority queue we cannot do that, so we will have to use set for this. Okay, we will be using set for this. Okay, we will be using set for this. We don't need this or this. I don't need this. Okay, maybe. I don't think we need any DFS here. It's extra, so we can do it here also only. So we will create a adjacence matrix first, then we will take the weight input, then put the weight here. Okay, done. And remove all this. Now we have a distance array. Okay, and we have our set. Say PQ. Okay, we will insert our starting node. Okay, uh, we will start, we will extract this. So what do we call it? P is basically pq dot begin. Okay, and we will remove it. Okay, so this is done. We have the node, its distance and all. So if we see that reaching this node, so basically if we see that the distance for reaching this current node is greater than what we have already encountered, or what we have already calculated, calculated, then you will not do anything. Otherwise, what we'll do, okay, our adjacency matrix contains node and distance. So some these are like just opposite, so you need to keep that in mind. So basically we need shortest, right? We need shortest distance. So 29. What is the limit? 29. Okay, it works. So we'll check if the distance reaching this node, or basically we need to do one thing, that is relaxation, right? So basically distance of reaching this node is minimum of distance of reaching this node and the current distance plus node dot second, basically the edge weight. Okay, and when we have set this, we will push it in the priority queue, priority set. So like this only, and after that we will print the this like answer. Okay, so before adding, I will check what we will check. We'll check what we will check if we'll check if there are any duplicate if there are any duplicate here. So basically this. Okay. Distance to start. Okay, this should be 0. No, but this is 0. We are starting with 0. Yeah, we are starting with 0. So we started with 0 and 1. Okay. What is the current size of priority queue right now? Okay, after removing it will be 0 only. And we went to the third and then second, so both of them are traversed, so they are there only in the priority queue, but then again 1 0, so 1 0 again. Okay, so instead of doing this, we will check whether if distance node.ff is less than is greater than your distance to this node plus node.ss, then only, in that case only, we will insert this. Okay, otherwise we will not do it. So we have our solution It was actually simple, but uh, my bad. Very silly mistakes here and there. Fuck. Oh, wrong answer. Why? Right. There is some problem with the code, I think. Okay, why is there 10? Okay, so okay, but then again, so if it is 1e9, I think we should go for Wait, what? Is this not a directed graph? Okay, so the issue was with the graph itself. Yeah, the issue was with graph itself. Otherwise, the solution is very similar to the last one. Okay. Length of the shortest route between two given cities. Length of the shortest route between two given cities. In the brute force approach, for every city we will do the Dijkstra, and then we will process Q carry. So it will take like NQ log n, right? So we have this. So we, in the brute force, for each node we will do Dijkstra. So it will take what, n log n, n log n or n log m. Okay. So n log m. What is Dijkstra's time complexity? E log Dijkstra time complexity. V plus E log or E log V. So we did this. The best is E log V. So m log n. M log n. So Q m log n or Q n log n. Oh, sorry. Q n log n. Okay, so this is not feasible because Q can go from, okay, so it will go from 10 to the 5, we will go from n square, so 10 to the power 7, and then log n it will take, okay, so it is n square, not 10 to the power 2, not 100. So n square means 25 into 10 to the power 4, right? So 10 to the power 9 into 25. Okay, so this will not work. Brute forcing will not work. We need to do something else. And what is this? Achha, this is query. We can do there are different shortest path algorithms, like for example, for a non-negative weighted graph we can do Dijkstra, which is a single point source algorithm, single pair shortest path, SPSP. And for multiple, or if you want to calculate the distance in pairs, then we have your Floyd Warshall, I guess, Floyd Warshall, or you also have your Bellman Ford, I think. So Bellman Ford takes n cube, and it will be 1.25 into 10 to the power 8, so that will work, or it may be, yes, it will work. So Bellman Ford should work. Floyd Warshall, I'm not sure. Floyd Warshall. So we have this. So we have Floyd Warshall and Bellman Ford. So Floyd Warshall we can use. You can also use Bellman Ford. I do not remember how did the algorithm work actually. I remember some of a little bit of Floyd Warshall. I think it is basically like a DP. So we can have a Floyd Warshall. So if we calculate a distance, let's say dpab, it is actually the minimum of your dpa b, and then your dpa k plus dp k b. So we choose intermediate nodes and try to find the minimum that way. So dpab of course represents the minimum distance from A to B, and for example, if we have a graph like this, where we can go in this and we can go like this. So if I do dp13, right now it will be set to 4, and if I relax it, then I'll try to iterate all the possible nodes. So I will do like dp1 1, and then I will try to choose different k values. Okay, so basically over all k, okay, we will choose the minimum value for this summation, and then should see. So here k can be 1 itself. If k is 1, then dp of 1 1 will be 0 and it will be 1 3 only, so there is no point. If k is 2, then it will be 2 3 1 2 2 3, so it will be 1 plus 1, so it will give me 2. Right now it is giving me 4. Okay, and if it is 3, then it will be 1 3 and 3 3, which is 0, and so it will again give me 4. So the minimum that I was able to find is 2. So this is how Floyd-Warshall works. Bellman-Ford is also similar. There are n-1 iterations for initial edges. Bellman-Ford is actually used for your cycle detection, I think. Bellman-Ford use. Okay, so Floyd-Warshall will work. And okay, so I will implement Floyd-Warshall. Floyd-Warshall. We have the graph here, and we need dp. Oh, sorry. We need dp, and this thing will move. So okay, is it two-way roads? Okay, two-way roads. Then we need dp, so dp, we need a 2d dp. Okay, so need a 2d dp, and the size will be everything is set to -1 right now. Okay, and here I will set for all values. Some base cases. Basically it means going from 1 to 1 itself will be 0 distance only, so that kind of things. I should mention this here. So dp AB means minimum distance from A to B, and this is our state, this is our transition, and we need base cases. Okay, so dp I will be 0. Other than that, we can populate the entire matrix with initial values. Hmm. Initial values we can do, so it will be okay. We also have q. Okay. We will define this here. We will initialize it also. But here we will initialize with 1e14 because we want to find the shortest distance, so we need this, and it will be 0. And here what we will do, we will do dp ab as well as dp pa to be minimum of dp ab and c. Okay, so we have initialized the dp as well. Now we will just do the rest. So we have this, we have k going from 1 to n also, and we will do dp ij is minimum of dp ij dp ik plus dp kj. Okay, and this should work. And for all the dp states where the value is still 1e14, we will set it to -1. Okay, and I think this should work. Okay, minimum of dp c. 558 minus 1 3. Okay. Some wrong answers here and there. Okay, 52594, 52554. We don't even need this. Just a waste of resources. I think I'm doing some mistake in here while setting the initial values. What if I set it to C only? I've compressed these two steps. Okay. Maybe that is the issue. Okay, so instead of doing it inside, Okay, so the issue was with the order only. The rest was not an issue. This order was the issue. Next, high score. Play a game, n rooms, m tunnels, 0, x, positive, negative. Task is to walk from 1 to n. What is the maximum score you can get? Bellman Ford, but sorry, Floyd Warshall, but for 2 rooms only, 1 and n. So, is it possible to do it using Floyd Warshall? I don't think so. I think this is a Bellman Ford algorithm. But that was it for today. I think we saw all the shortest routes, and monster we will do tomorrow. Yes, tomorrow. Tomorrow is Thursday, and we will solve monsters on Thursday. Okay, so there is not anything that I want to discuss other than yeah, there is nothing. So yeah, that was it for this stream, and we will meet tomorrow. Till then, take care and